All right, so the next part of Chapter 18 deals with chemical equilibrium and reversible reactions. So up to this point, we've talked about chemical reactions as if they always go from reactants to products, which is an oversimplified view of how most things occur. There are many chemical reactions that do not occur completely in one direction, but they are said to be reversible. So what does it mean to be reversible? Well, it would be a chemical reaction where the conversion of reactants to products and the conversion of products to reactants can occur simultaneously. But when this happens, generally speaking, there's a favored direction. So either the reactants will be favored or the products will be favored. Okay, so the classic example of this would be the production of sulfur dioxide or trioxide from sulfur dioxide and oxygen. So let's use our friend that we saw in the last section that illustrated activated complex. Let's use it to illustrate forward reaction, reverse reaction, conversion of reactants to products, and conversion of products to reactants. Okay. So if we look at this illustration here, we have sulfur dioxide combining with oxygen to produce sulfur trioxide. Okay. And the breakdown of sulfur trioxide into sulfur dioxide and oxygen. So we get the production of reactants into products and the production of products into reactants. And then at this state called equilibrium, there are reactants and products. But as you can see, there are more SO3 molecules than there are O2 and SO2 molecules. So this equilibrium favors the products. Okay. So what is equilibrium? Well, if you look at the reaction casually, it would look like the reaction has stopped, but it's actually a dynamic equilibrium. It's a state of balance where the rate of forward reaction and the rate of reverse reaction are equal. So when an equilibrium occurs in any process, you want to be thinking, what is an equilibrium? What is equal? Well, in this case, the rates are equal, so there's no net change. It's not that the reactants and products are equal in amount, it's that the production of reactants and products, the rate of production is equal. So at equilibrium, it gives the appearance that the reaction has stopped, but rather it's a dynamic state where the forward and reverse reactions are occurring at the same rate. So if you think about the number of people in a gym during a basketball game, before the game, there's a flow of people into the gym. And then once the game starts, it's not as though everybody stays in their seat. Some people get out to go to the snack bar. Some people get out to go to the bathroom. Some people just can't sit still and they're there for the social scene. So they're just constantly going in and out of the game. Okay. But once the game starts, there's generally a pretty static number of people in the gym. Some are going out, some are coming in, but for every person that leaves, another person comes back in. Okay, so here's a graph. There's actually two graphs here, one of the forward reaction and one of the reverse reaction. So we can see that the reactants are at time zero. Okay, so we have a lot of these two things. We have SO2 and O2, and if you look, we have twice as much SO2 is O2, and if you look at the balanced equation, 2 moles of this for 1 mole of this. So there's twice as many SO2s as O2s. Then as the reaction goes, their concentration goes down and the concentration of SO3 goes up. Okay, so where would you say equilibrium is? And most people would casually say, oh, equilibrium is where the numbers, the amounts are equal, so it's where the lines cross. No, that's not it. Equilibrium occurs when it looks like the reaction has stopped. So when the lines level out. Okay. So the amounts stop changing. So the rate of the forward reaction, the production of SO2 and O2 to SO3 equals the amount of SO3 turning back into SO2 and O2. Okay. So where the lines level off. So we would say that the equilibrium point is at 2.2 units of time. And here the reaction rate is, the reaction is reversed, where we're starting with a lot of SO3 and we're ending, or the SO3 decreases as the SO2 and O2 increases. Now, one thing that's interesting, notice that the equilibrium is at the same time and the equilibrium concentrations are the same. So here's another equilibrium. It's the equilibrium between hydrogen and iodine to produce hydrogen iodide. So we start with equal concentrations of these two, and we actually have numbers here, 1 mole. And here we have no hydrogen iodide, so this is the product. So as the reactants diminish, the products increase. And here again, the forward reaction is favored. There's more product than reactants at equilibrium. Okay. Now, here's the same reaction, but instead of graphing the concentration over time, it's graphing the rate over time. So here we're starting with a fast rate and a slow rate. This would be the forward reaction, where reactants are turning into products, and as the reaction goes, it naturally slows down the longer it goes. And then the reverse reaction starts slow and then speeds up, and then at some point the rates are equal. So this time here would be the same as this time here. Here we're graphing the concentration over time. Here we're graphing the rate over time. Okay, so the equilibrium position can be figured out by which has greater concentrations, which is there more of. Here the concentration of the products is greater than the concentration of the reactants. So the forward reaction is favored. But if at equilibrium there's more reactant than product, then the reverse reaction is favored.